Hey everyone. So this is quick tutorial where we'll explain how Reinforce, which is a reinforcement learning algorithm works. Um, I will walk through kind of a bit of the math behind it, trying to get an intuition for why we do certain things the way we do it. And then I will walk through an implementation that I did um, in order to show that it actually works. um, on real problems. All right, so reinforcement learning. I would assume that you're already familiar with what reinforcement learning is. Um, Reinforce is a policy gradient algorithm, which is different from um, non-policy gradient algorithm, for instance, Q-learning, because in Q-learning, the policy is implicit in our Q table or Q function. So we have a Q function that will take the state and action and output some kind of quality of that state action. Now, this Q can be a table, so then we will have row as state and action in the columns, or it could be a neural network or whatever, or a linear function or whatever you like. The important thing is that to pick the action that we want to do and basically find our policy. So our policy pi of our state will be the argmax over the action of QSA. So in the case of Q learning, the policy is implicit in our Q table. And then in our algorithm, we find a way to update this Q in order to get a policy that maximizes the reward. Now, I'm explaining this because this is not what we do in policy gradient. Instead, in policy gradient, we we have a policy, and we parameterize the policy and run directly updates on the policy itself. This gives us a bunch of advantages. The main one is that since we just give the state to the policy and get out an action, we can have a policy over continuous action space. This was not possible in standard Q learning because if the action space was continuous, then taking this max is an optimization problem in and of itself. Like you would have some kind of function from action to quality, and you would need to find the maximum of that function, and that's an optimization problem itself. Instead, if we have directly a policy, so the policy is not implicit in our Q table, but we have directly a function pi of theta, where theta are the parameters of our function, that given a state gives us the action that we need to do, then we can even have a continuous space of action, such as, I don't know, the angle at which I move my arm, and get directly the action that we need to perform. There are a bunch of other advantages, like it can be shown that this policy gradient algorithm converges a bit faster, but I think this is the main one. Okay, so since we want to directly optimize our policy to maximize the reward, we need to something to optimize. And we'll call the function that we want to maximize g of theta. So it takes theta, which are the parameters, like they are the parameters that parameterize our policy. So if our policy is a neural network, this will be the weights and biases of the neural network. And the function that we were trying to optimize is just the expected value over the trajectory sample from our policy of the reward of the trajectories. So basically, what this is telling us is we would like to maximize this function, which is the expected or like mean value over the whole distribution of trajectories given our current policy of the reward. So like the more we would like to change our parameters theta in order to get more reward with the policy that we get with those parameters. Now we can rewrite this as an integral, so that will be the integral of the probability of the trajectory given multiplied by the reward p of t. And okay, so as in any machine learning a machine learning problem, in order to optimize this function, we will need to take the gradient. So we take the gradient of this with respect to theta, and this is what we get here. Now, computing this thing here is not easy at all. The reason is this is an integral over the whole distribution of trajectories, and if our environment is a bit complex, there will be like an infinite number of trajectories. And so in order to compute this integral exactly, we would have to know the probability of all of these trajectories and the reward of all of these trajectories. So given a certain policy, we would kind of need to roll it out so many times in order to get these values. And this is not feasible. Now, it would be great if we could apply some kind of approximation method like Monte Carlo methods. But in order to apply those, we would need to have a probability distribution, because the way Monte Carlo method works is that we have a probability distribution. We would like to approximate the mean of this probability distribution. And so we keep getting samples from the probability distribution and then take the mean of those samples. And for the law of large numbers, we know that we will eventually, as the number of samples increase, we will eventually converge to the true mean of the distribution. But we cannot do this here because this is not a probability distribution. These are just gradients. Okay, so what we can do, this step that I'm going to do here is called the logarithm trick, and is a way to solve this problem. So first thing, we can bring the gradient in. This is for the Leibniz integral rule. And this kind of simplifies a bit things. And now we notice something. We notice that if we take the gradient of the logarithm of our probability of the trajectory tau given theta, this is the gradient of p tau theta divided by p tau theta. And so if we bring this to the other side, we can substitute our gradient of p tau theta with p tau theta gradient logarithm p tau theta. So equals, okay, so it's p tau theta gradient of the logarithm of p tau theta reward and everything as before. Now, this one and this are exactly equivalent. But the cool thing is that this is a probability distribution. And this is an expected value. It's the mean over the probability distribution. So we can rewrite it as the expected value of all of these. And now we can apply our Monte Carlo sampling method to this. And the way we would do it would be by just taking samples of this and then taking the mean. Now, there are a few more things to say here, because, so just to repeat, we're taking sample from this thing here, but I would like to get into a bit more details of what is each of these terms is. So this logarithm of p tau theta, so this is the probability of a certain trajectory given the parameters theta that parameterize our policy. But the probability of a certain trajectory doesn't just depend on the parameters of our policy. There are a bunch of other things. The first one is the probability of our starting state, S0. This is log multiplied by the probability, sorry, the multiplication from t equals 0 to t big T minus 1, capital T minus 1, of the probability that our policy assigned to action AT given state ST multiply by, and here we also need to take into consideration the probability in our environment, because given a state and an action, I might end up in different state by taking that action in that state, because our environment has some stochasticity that by even taking the same action from the same state, I might end up in other states. So we need to take that into account, and here we multiply by the probability of ST plus 1 given ST AT. But the cool thing is that by having the log here, a lot of this stuff simplifies, because the logs turns multiplication into addition. So this becomes log, logarithm of the probability of starting S0 plus logarithm of the sum from t equals 0 to t e minus 1 of the probability of each of the action for our policy, plus the logarithm t minus 1 of our probability of the transition in our environment. I'm not gonna copy it, but it's the same as above. And a very cool thing happens here, because in our original function up here, we're taking the gradient with respect to theta. Here I missed a theta. And this thing is this thing here, the logarithm of the first state, is constant with respect to theta. So in the gradient, we can remove it. Same thing for this one. And so we can rewrite our expectation over the trajectories sample from our policy as the gradient of the logarithm of the sum from t equals 0, t minus 1 of this thing here, which is very nice. We have basically removed this term here, which would have been very, very not possible to compute, because if our environment is very complex, we don't fully know what is the probability of a next state given an action. It's not something tractable to compute. Now, I would like to address this other term, the reward of a certain trajectory. This is simply, now this depends on the environment that we are using, like if we get the reward at the end or during and so on. But in general, it would be something like a sum from t equals 0, t minus 1 of the rewards at time t discounted by a factor gamma to the power of t. why do we put the discounted? Well, this is standard RL, but we would like that in the future, we like the reward in the far future are much less important to the current state action pair. Otherwise, we will give too much importance to those, and those don't depend too much on the current action that we're taking. So we can rewrite one last time all of this. And this again is the gradient of j theta. And I just need to substitute this here. And then once we have the gradient, this is basically done because we can update our parameter theta, which again parameterize our loss, using standard gradient ascent in this case, because we are trying to maximize the rewards, we need to go up. So we do plus. And in this case, this gradient would be just computed using torch and auto differentiating functions. Okay, I will quickly show the implementation that I did of this reinforce. So this is just a policy, which is a small neural network, which takes in the dimension of the state space. Just have one hidden layer and then the output. Okay, and this is the training. I'm using CartPole V1. It's a very simple environment where we're trying to balance a pole on a cart. Here I'm just defining the optimizer and TensorBoard and so on to the interesting part. So for all the epochs, we first reset our environment, then we run a rollout over our environment. So we start from an initial state S0. Our policy, which is our neural networks, give us an action and gives a probability distribution over the action. In this case, there are just two actions, either left or right, to balance the cart on the pole. So we use this categorical and then take a sample from the distribution. We perform the action in the environment. We get a next state and a reward. So we can collect the next state and the reward. The new state in which we're in is the next state, and we keep going until we terminate. Then we compute the discounted reward. This is slightly different from what I showed before, but the intuition is the same. So G, which will be then inserted in our returns, collects the discounted reward so far, and we start from the end. So the very last element will have G0 and will have only the reward. And this makes sense because the very last element doesn't have anything ahead of it. So the only reward the only reward for that action is the reward that we get on that step. Now, the element before will have G, which will be the reward at the very last step, plus the reward at the very last step discounted by gamma, plus the current reward at the second last step, and so on backwards, so that each action in our trajectory will only get the discounted reward for all the following actions. We turns the returns into a tensor, and we normalize it by the mean of the tensor. This is quite important because reinforce is known to suffer from high variance over the estimate of the gradient. That's because like there is a lot of stochasticity in this estimation here. There's stochasticity that comes from the environment, from the fact that taking the same action from the same state could lead to different result. There is stochasticity from the policy that like the same policy we could sample and it would give different result. And there might be other form of stochasticity. And all of this leads the gradient to be very high variance. Like the yeah, the same parameter theta could give rise to very different gradients. And so we want to find a way, and so the update will be always in different direction. So we want to find a way to reduce this variance so that we try to go more in the right direction of updates. And one way to do it is to just subtract the mean and well, you can also normalize with the standard deviation, but this is the important step in order to minimize the variance and do the updates in the right direction. Here we're effectively doing the formula that I explained before, where we multiply the log probabilities that we saved here with the reward normalized. And we have our epoch loss, which we save in this, which we save here. And then after certain number of steps in the batch sizes, we take the mean loss over the batch. This is another thing to mitigate the high variance of the gradient, because if you take a few gradient in your batch and then take the average, you are more sure that you're going the right direction for the updates. We compute the gradients, we do our step in the optimizer, and that's pretty much it. And this works decently. I mean, it's not perfect. You can see here the episode length. And you can see here the high variance of our reinforced algorithm, because different episode, sorry, different training run leads to very different results. Like we always reach kind of the top, and then maybe there is some catastrophic forgetting here with the yellow, but it varies a lot from one run to the other. And yeah, and this is in part attributed to this high variance problem of this algorithm, which is then mitigated in other algorithm that came later, like TRPO, PPO, and so on. But yeah, this is pretty much it. Hope it was somewhat clear. I will leave the link to this GitHub code in the description. And yeah, thanks for watching. Bye.